So we will start the second part of this presentation. Here we see the pedigree where we identify that the fifth child is a recombinant and the recombination frequency is 0.2. It's exactly the same example we covered in the first recording. Now, a very interesting question is that, is it really theta 0.2? Okay, 0.2 for this family, yes, we are certain about it. But is the distance 20 centimorgans between this marker and the gene causing the disease? If we look at another family, will we still find that theta equals 0.2? For example, this is the Smith family. We identify another family, the Jones family, but the Jones family have two children. Let's assume that the two children from the Jones family have the same genotypes. Do we see recombinants? No. So for the Jones family, theta will be 0. For Smith, theta is 0.2. If we did a third family, maybe because each event is independent from one another, maybe they had one child, and let's assume that the child had the genotype homozygous for allele 2, but affected. Or even if they have two children, the fifth and the fourth, that family will tell us that theta equals 0.5. So the theta that we see here and the distance that we have estimated, it is based on one family and one genetic marker. And although these examples that we present here are very good for our understanding the principles behind linkage, in reality, when we design the linkage study, we want to use as many families as possible, and we want to use a large number of markers to scan the genome, to conduct, in other words, a genome-wide linkage study. And we could see here an example where I have entered more than one marker along the chromosome. So you could see that the affected individual in generation 2, individual number 2, we could see the genotypes for 5 markers, A, B, C, D, E, and this individual is heterozygous for all these 5 markers, A1, A2, B1, B2, C1, C2, D1, D2, E1, E2. So when we look at the third generation, we will see that individual progeny number 2, the genotype for marker A is A1, A1. So recombination, we see a crossover we have at this point between markers A and B, and therefore this individual is a recombinant. The same for individual 5, progeny 5. So if we draw the lines from where we see recombination and where it ends for individual number 5, you could see the advantage of going through the transmission patterns, the genotypes for all individuals, the affection status. It will help us narrow the region and localize the gene, the gene region that is likely to harbor the gene that is responsible for the disease in question. Linkage analysis can only identify the significant linkage region. We did say on the first recording that we have 22,000 genes in the genome. So there will be many genes in that, between that distance, between the red lines. But it's the first step that it tells us that we need to look at that specific chromosome, and within that chromosome, we need to look at that specific region. So this is the region that is likely to harbor the gene for the disease. So we could study further that region, and in fact we do have techniques to study further this region through fine mapping and identify the gene. So this slide gives an overview of what needs to be done when we use a large number of markers. But I did mention earlier on the problem with theta, so we need to conduct linkage analysis with as many families as possible. So it is important to have a statistical measure that will give us the confidence to say, yes, there is strong evidence of linkage. Again, with the example that we saw earlier on, yes, we do have some evidence, but we are not certain. It could be by chance. So we are using a lot score, which is a log of 10 of a ratio, the probability of observing this particular family if these genes are linked, and the probability when we assume that there is no linkage. It's very important to understand the load score, not only because you understand the foundation, the principles behind the linkage analysis, but also it will help you interpret the results that you see in the published literature. So let's do a load score analysis step by step. Here we are looking at a diallelic marker, 2 alleles. The marker's ID is IF10, and this is the marker that was identified, that was linked it was identified in the linkage region that helped to identify the NF1 gene, the gene responsible for neurofibromatosis type 1. The marker and obviously the gene are located on the Q arm of chromosome 17. Now, I'm already telling you the gene, but let's assume we don't know the gene. It hasn't been identified, and we want to do so in our study. So you see here the individuals that they have neurofibromatosis type 1, and we were very lucky. We are just be given genotypes of the IF10 marker to study, and we want to identify whether there is linkage in this region. Again, the IF10 marker is located in the Q arm of chromosome 17. Now, when you look at this pedigree, do you see any recombinants? No, there are no recombinants. Let's start from this individual here. 1 came from the healthy mother, 2 came from the affected father. So, under the assumption that there is linkage, capital D will be on the same haplotype with 2, and every individual that we see in the 3rd generation with 2, then we do expect the individual to also carry, to also have the disease under the assumption that there is linkage. So the 2 here came from the healthy mother, but 1 from the father, unaffected, no recombinant. 2 came from the father, also affected. 2 affected, no recombinant, no recombinant. 1 with small d, non-recombinant. 1 with small d, not recombinant. So let's estimate the load score, this ratio, the probability of observing this family here. If the gene with alleles capital D, small d is linked with the IF10 marker, divide by the probability of observing the very same family if these 2 are not linked. Now, The observed theta is 0. We have already established that there are no recombinants in this family. But we still need to test the hypothesis. We have to estimate the load score for different hypotheses. So here, we could make it very simple and test the hypothesis that theta equals 0. Observe theta 0, but we also have an initial hypothesis that theta equals 0. Because, okay, it's 0 in this family, the Smith family, but if I go to Jones family, maybe I will see a recombination theta of 0.2 or something else. We do not know the real theta that exists in the genome. Morgan did obtain a very large number of progeny, if you remember the slide that we covered. Here we are only looking at one family, and okay, the observed theta is 0, but it doesn't mean that the same theta will be observed in another family. So we really need to test the hypothesis. So we hypothesize for simplicity that theta equals 0. But if you think about it, because we covered recombination is essential for chromosome segregation, and it occurs during meiosis, you do expect recombination. So theta is not really a very good assumption to make to a starting hypothesis, but it will help us step by step to estimate the load score, and then we will see how the load score is estimated when theta is not 0, when we test the hypothesis that theta is greater than 0. So the father here can only transmit two possible combinations. Either capital D with the red allele 2 or small d1. Small d1 was inherited from the mother. So the D1 haplotype was inherited from the mother. And capital D2 was inherited from the father. Now, the possibility of each of these events to be transmitted to the next generation is also 0.5. This individual, under the hypothesis that theta equals 0, so you could see the importance of estimating a load score under a specific hypothesis, is either 1 or 2. 1 with small d, 2 with capital D. So transmitting this or the other is 50%. Each event is independent. 50% chance here, 50% here, 50% third, and so on. So when we look at the load score and the ratio, the probability of observing this family is 0.5 in the power of 5, because we do have 5 progeny. Now we need to divide this probability, we see here, with the probability of observing this family when the IF10 marker is not linked with a gene that is responsible for neurofibromatosis type 1. Now, this is straightforward, really, because if IF10 is transmitted totally independently of the NF1 gene, then you do expect all possible combinations. If the marker with alleles 1 and 2 is totally independent with the transmission of the gene with alleles capital D, small d, then you do expect this individual to transmit either capital D1, capital D2, small d1, small d2. So there are 4 possible scenarios, 4 possible arrangements, 4 possible combinations. So here we have 2 possible combinations, capital D2, small d1, and here we have 4 possible combinations, because if capital D small d is independent with 1 and 2 of the IF10 marker, then we do end up with 4 possible combinations that they could be transmitted. So at 0.25, again, its event is independent. So at 0.25 in the power of 5. So the ratio is 32, and the log 10 of that ratio is 1.5. So here we have a measure that is more accurate, but by looking only theta and concluding that there is evidence simply because theta is lower than 0.5. So estimating the load score is essential. And what we take as a strong evidence of linkage is anything that is above 3, a load score of 3 and above, equals 3 or above. And I will cover that in a moment. So now one could say that, okay, I don't have linkage, even though I didn't have any recombinants. The load score is below 3. Yes, but it is half that, is 1.5, only using one family. Again, our study design will include more than one family, so we add the loads together. So 1.5 is indeed a very, very high load. There is a very strong evidence that there is a linkage, but again, we cannot really make the final conclusion only in that family. But 1.5 from one family is indeed high, and we have taken the very simple hypothesis that theta equals 0. Now let's use exactly the same family, but make the 5th child recombinant. We keep exactly the same genotypes as before. So this individual has allele 1, the green allele, that was inherited from the grandmother, was passed from the grandmother to the affected son, and the son transmitted it to the 5th child. But we have capital D, so it's a recombinant. The observed recombination here is 0.2, 1 out of 5. But let's test the hypothesis that theta equals 0.1. Again, 0.2 as theta is specific to this family. In another family, it will be different. So we want to establish what is the most likely theta between IF10 and the gene NF1. Now, this becomes a little bit more complicated here, but because we have done the previous example with theta equals 0, I think it will be easier to follow what we need to do to estimate load for theta equals 0.1. So this individual will still transmit the 2 possible haplotypes, capital D with 2 and small d with 1. But that will happen 90% of the time. There is another percentage that we need to take into account, that this 0.5 is the probability of transmitting one or the other. But we need to take into account the hypothesis. So 90% of the time, one of the 2, capital D2 or small d1, but 10% of the time, capital D will be with allele 1. So the probability of inheriting the disease allele with marker allele 2 is 0.5 times 0.9, and that gives 0.45. The events are independent, so 0.45 times 0.45 times 0.45 and so on, in the power of 4, because we have 4 non-recombinants. And then we want to include the one recombinant that we have identified here. So that will be 0.5, the recombinant chromosome or the other haplotype, 50% chance. But theta is telling us that this will happen 10% of the time. So that is 0.05, and it's multiplied with the outcome that we've mentioned earlier on for the 4 non-recombinants. The denominator of the ratio stays exactly the same, because if we estimate the probability of observing this family under the evidence of no linkage, we still are talking about the 4 possible combinations, and we're still having 5 children. When we are assuming that there is no linkage, it doesn't really matter how many recombinants or non-recombinants we have. So you could see that with this hypothesis, 0.1, the load, and only with one recombinant, the load score from 1.5 is reduced to 0.32. We need to estimate the load score exactly the same way as we have done here, but for different thetas. And this is a classical table that we see in our textbooks and published papers. We are estimating the load score for different hypotheses. The highest, the load score, will be attached to a theta which is likely to be the one that is real. So this process of estimating a load score for different thetas, coupled with the fact that you have more than one family, let's say you have 20 families, and in addition to all that, you're doing the load score for different families, you then can see how a detailed linkage analysis is and the power that brings to us to identify the linkage region in the genome. By the way, when you look at this table, you do see 0.32 for the example that we've done here, but the highest load is for this recombination frequency. And indeed, these load scores are based only on this family, and the observed theta is 1 out of 5, it is 0.2. So we received the highest load for that. But I would like to iterate again, and we will cover all that in the live tutorial session, that in reality, theta cannot be estimated from one family alone. I mean, yes, it can, and in this case it's 0.2, but it doesn't mean that we will find the same in another family. In other words, we cannot establish that we are having 20 centimorgan between IF10 and NF1 in the genome. One family is not enough to conclude that this is the centimorgan genetic distance. So one family can tell us the theta for that family. But the genetic distance between the IF10 and NF1 needs more family data to make a concrete evidence, and we need the load score for that. So why did we take the load score above load score as a strong evidence of linkage? Because log of 3 corresponds to 1,000 to 1 odds in favor of linkage. So the log 10 of 1,000 is 3. So 3 and above is a strong evidence. So we do have a linkage map, and I'm showing here the centimorgan map. The name is the same, whether you call it linkage map or centimorgan map, we mean the same thing. From chromosome 9. So you could see here the macrosatellite markers and the genetic distance between them. So 0 to 50, there's 50 centimorgan distance between this marker located here with the first marker located here. And you could see the difference between female centimorgan and male centimorgan. So a proper linkage analysis, in order to conduct a proper linkage analysis, then we need to collect as many families as possible, scan the genome with a large number of markers, conduct whole genome linkage analysis, and then the linkage region that will be identified, it needs to be followed up with fine mapping using SNPs. And then you could publish. So linkage is very important because when you know that A and B are linked, there's strong evidence of linkage, then by looking at the haplotype for this individual, the unborn baby, you could include that, and assuming 100% penetrance, that the unborn child will have the disease after birth. So we did mention penetrance. Penetrance is an important factor that complicates our interpretation about the patterns of inheritance in a pedigree, but it also is a problem when it comes to load score analysis. But because monogenic disorders, they are characterized by very high penetrance, so this is also a reason why linkage mapping has been so successful, and we have identified so many genes for monogenic diseases. I showed you that slide from the website OMIM on my first recording. So linkage analysis is extremely powerful, but it does have problems as well. Often it's very difficult to find the exact pedigrees. The biggest problem with linkage analysis is that it cannot really point to a specific gene in the genome. It can only give you the linkage region. In some examples that I have seen, the linkage region is really very big. In some cases, even the entire arm of one chromosome. But at least you've managed to zoom into the genome and identify which chromosome is involved, and which the region that is likely to contain the gene responsible for the disease. I'm also mentioning here locus heterogeneity. If we start moving away from monogenic disorders, then we are talking about more loci being involved, more genes being involved, and that will give rise to many linkage regions. So locus heterogeneity is a problem. The reason why I'm mentioning this is because at the 20 years ago, people were still using linkage for complex disorders that they are polygenic, because it was a very good, well-established tool that we have in our hands, and we wanted to use it even for complex diseases. But if there is no locus heterogeneity, then linkage works well for monogenic disorders, as we have established, but these are very rare when you look at the frequency compared to polygenic diseases that are very common in the population, and we have a large number of them. So the more you move away from monogenic and you start having, you start adding more genes, then load score analysis will start giving many linkage regions. It is very difficult to interpret the results. Again, we covered all that. We did cover penetrance, but we did say that monogenic disorders do not have such problems compared to polygenic. And as a result, because of that, it has been used even for polygenic diseases such as Crohn's. So this is a publication from 2001, so almost approximately 20 years ago. And we could see that what they have done is that they have plotted on the y-axis the load scores, and on the x-axis we see the, the markers that we have on the linkage map. So we know that this is a 31 centimorgan region. So you could see that the linkage region 3 and above spans a very large region. 1 centimorgan is approximately 1 megabase. So here we are talking about a multi-megabase region, really very large. Nevertheless, even though it was a complex disease, linkage analysis still managed to identify NOD2, one of the very important genes, the first genes that were identified for a complex trait. Crohn's disease is a polygenic disease. It's a chronic disease with high prevalence, 100 to 150 per 100,000 populations of European ancestry. So a decade after, actually, yeah, almost a decade after the linkage analysis that they have identified the NOD2 gene, the Wellcome Trust Case Control Consortium conducted a study with 500,000 of single nucleotide polymorphisms scattered across the genome. Here you could see the centromere, chromosome 1, chromosome 2, and here you see the significance level, the log 10 of the p-value. So even though they've used a large number of patients, approximately 2,000, and a large number of controls that don't have the disease, approximately 3,000, they still found NOD2, but it has been already shown previously with linkage. Linkage didn't identify these regions, these signals here, but it was powerful enough to identify NOD2. But this output, obviously, from linkage to identify one locus was not enough. Hence the reason why we are now conducting large-scale studies in case and controls. But linkage still is the method of choice when it comes to monogenic rare diseases. So for the live session, we will go through load score analysis using human pedigree data, but it will be good to also cover genetic risks. It's always very important to be able to work different scenarios and try to estimate the risk. So for the live tutorial session, we will cover linkage, but please revise Hardy-Weinberg because we really need to do some exercises on that as well. So the book that I've mentioned, that you have been given, Strachan and Reed, Human Molecular Genetics, is a very good textbook. So here I'm giving an example on autosomal recessive disease, cystic fibrosis. So 1 in 2,500 babies in the UK do have cystic fibrosis. So we want to calculate the expected frequency of carriers in the population in the UK. You have already covered Hardy-Weinberg, but we will cover it again. So please revise this material. And as I said, in the next live tutorial session, we will go through linkage and also frequency of carriers using Hardy-Weinberg. Human molecular genetics covers the material that I presented here, but also it will be a very good textbook for your entire course. An additional good book is Medical Genetics by Jordi et al. Thank you very much, and I shall see you at the live session.